We propose LiP-Flow, a novel approach for learning conditional priors for high-fidelity and animatable 3D face avatars. Our work aims to build an avatar model that allows for view-conditioned image synthesis. To be able to convey emotional states of users, our focus is on learning an expressive avatar model that can capture facial dynamics and fine-grained details. Such photorealistic neural avatars are typically trained with multi-view data captured in camera DOMs. At Inference-Time, however, we have access to only limited inputs, such as partial images from head-mounted devices, abbreviated as HMC, or sparse facial landmarks from a front-facing camera. And we want to be able to control the avatar via such limited driving signals at runtime. A typical approach is training the Inference-Time model separately. We argue that this makes the main avatar model unaware of the limited inference-time settings. In this work, our main contribution is incorporating the inference-time model into the training pipeline of the main avatar model by learning a bijective transformation between them. Here we have two main constraints. First, the reconstruction quality of the base model should be preserved when we incorporated the inference-time encoder. Second, the inference-time encoder should learn informative representations from the limited inputs. The primary challenge is the information asymmetry between the two input domains. Our work extends the prior work of Lombardi et al., the deep appearance models. The training time encoder projects the mesh and an average texture across all available camera views onto a lower dimensional latent space. The decoder reconstructs the mesh and predicts a view condition texture given a latent sample and a view direction. The training objective consists of reconstruction terms and a latent space regularization using a standard Gaussian prior via KL divergence loss. We introduce an inference-time encoder that is conditioned on HMC images or 2D keypoints. We then learn a bijective function via conditional normalizing flows that enables the transformation of latent codes from one space to another. We treat the inference-time encoders as learned conditional priors and train all the network components end-to-end. This makes the main avatar model aware of the limited inference-time conditions. Our approach replaces the KL divergence loss with the latent likelihood under the learned prior. This removes the similarity assumption of the KL divergence objective and allows the encoders to learn a more expressive and flexible latent space for the underlying task. At inference time, to further improve the quality, we can fit the latent codes to various types of observations. We first use our inference time encoder to estimate a conditional prior distribution, which is then used to initialize the latent codes. During iterative fitting, we calculate the reconstruction loss for the respective observation and evaluate the likelihood of the latent code under the estimated conditional prior. We compare our model with the base avatar model, DAM of Lombardi et al., and a latent code regressor. It is trained with direct supervision from the pre-trained training time encoder of the DAM. Here we evaluate the models by using HMC observations. For a better comparison, we flip the reconstructed and the ground truth images. On challenging expressions like this one, we see artifacts in the baselines. Our model learns the facial dynamics better and provides higher quality reconstructions. Even on the neutral expressions like this one, the baselines have notable differences. Where our model is able to capture subtle expressions faithfully. Here we apply random perturbations to the headset camera pose. The baselines exhibit jitter and temporal inconsistencies. Our prior model is more robust to the noise in the HMC images. Finally, to evaluate the effectiveness of our flow-based latent formulation over the KL divergence objective, we replace our conditional prior with the standard Gaussian one. We visualize randomly drawn samples from the standard Gaussian prior. The vanilla VAE formulation lacks diversity and rendering quality, whereas our formulation achieves a more expressive latent space compared to the KL divergence objective, and hence our model generates more diverse expressions with higher quality renderings. Thank you for watching.